Hello, am I audible? Yes, anyone can
Yes,
just.
sir.
Oh, fine. So, good evening. It's not big. Um, just, just let me back this here from the other device. It's not updated here. Yeah. So, welcome to week 3 of the live interactive session of the brief introduction of microsensors. The course instructor is Professor Santanu Talukda from ICER Bhopal, and I am the PMR of teaching assistant Vikas Pandey from IIT Jodhpur. So this is a brief about me. This includes the class link, the YouTube channel where all these videos are uploaded, my contact details, and so we will be starting about how MEMS is made, like how MEMS are made, why silicon is used, and what are the techniques that we use for fabricating MEMS. Okay, so before starting, if you have any query or questions, anyone, you are free to ask. Yes, anyone? Any questions, any doubts, anything you were not able to understand even in the previous week, you can ask. Yes, anyone? You are able to hear me, right?
Yes, sir. I have seen 3 videos, sir, in the week 3.
Mm-hmm.
I have to complete another 2.
Yeah. So till whatever you have seen, is there any query or anything you would like to get clarified or something?
Uh, it is better if we have the solution for week 1 and week 2. We can see the mistakes, sir.
Okay.
In the week 2, whatever problem is given for that one,
Mhm.
I could not understand the answer. I thought that only one answer, but they have given with comma two answers,
Two
sir.
answers. Okay.
Mhm.
So actually, at the end of the course, towards the end of the course, the solutions will also be uploaded in the course itself. You will see that the solution of all the assignments will be uploaded.
It is better after. Within this week, it is better, sir. We can have the
Okay.
practice.
Yeah.
At the end means it will be a pressure on us.
Yeah. No, actually, that part I am not taking care of. That is being
Yes, sir.
taken care
Okay.
by like IIT Madras only. Okay.
Okay, sir.
So I am able to take care of this. We can discuss some assignments which has already been like whose deadline is already over, and we can discuss, not an issue.
Okay, sir.
Okay. So so for now, let's start this class where we will first be discussing the summary of things covered in this week, and then we'll be discussing some questions to clarify those things. So first thing is silicon in maths. Okay. So why is silicon used in maths? One is, we have discussed this a lot of times. One is abundant and cost effective. It is easily available since it is made from silica or silicon dioxide, or we can say sand. Uh, sand. The base material is kind of sand. Okay. It has very good mechanical properties like have high young modulus and low thermal expansion that makes it well suited for making physical structures. As well as one very important thing is it is compatible with existing CMOS fabrication. That means the existing chip manufacturing, the semiconductor fabrication. In that we are already using silicon. We already have developed some techniques of using fabricating silicon-based devices. So we don't have to invent the whole thing or don't have to like optimize each and everything. Many processes and uh, process as well as many structures are well uh, optimized. That gives us the reason of make using silicon, okay, for MEMS structures. So to start with, how the silicon crystal looks like. This whole thing is one very important thing of using silicon is that I, yeah, hello, are you slowed up? Can you mute yourself? There is a lot of noise. If you want to speak something, you can. You have some query, you can speak. Else you can just mute yourself. Okay. So silicon is a crystalline material. That means it has a uniform structure throughout its bulk. Okay, and this is a, having a cubic diamond cubic structure similar to FCC or face centered cubic. Okay, where if we cut the smallest like smallest unit cell, that is smallest part of the crystal, we will find a structure very similar to a face centered cubic. That means atoms on the corners of the cube with one atom on the face of the cube. As such, it is very similar to face-centered cube. Here, since silicon we know has valency 4, so it is able to bond to 4 neighboring atoms, and that is a covalent bond. Since silicon is like 4, it wants to become 8, and that's why it will have a covalent bond, no ionic bonding, that it will not give electrons or take electrons, but it will share electrons with neighboring atoms. And as such, a very good covalent bonded uh, like covalent bonding is done, and each atom bonds to 4 neighboring silicon atoms. The crystal structure that forms is like this: diamond diamond cubic structure, or FCC, face centered cubic, which has a lattice constant, means the mean mean difference between two atoms at 5.43 angstroms. Okay, so when we are talking about these crystals, we will see something called crystallographic planes very frequently, in which, if we talk about silicon, 100, 110, and 111 are most commonly used planes in MEMS. Okay, and we will see that in fact these plates play a role, how the etching will happen, how it will be cut and it will not be cut. So we have to understand how this, uh, like what is this crystallographic plane. So if we draw a simple x, y, z, okay, so a plane that is here, say 1, okay, like it is, like each cube is 111, let's assume. So we will have, let's use some other colors like this. Okay. So now, if we make a plane, say like this, which crosses one point here, one point here, and one point here. So a plane like this. Okay. So in total, x here is 1. It is cutting x at 1, y at 1, and z at 1. This will, like what we generally do is that we take the intercept and then do a reciprocal to find the um, Miller indices. Okay, so we will call it as 111 plane. Whereas if you see this, another line I'm taking, yeah. Suppose that this plane we are taking. So we see that here it is cutting x at 1, but it is parallel to y and z plane. So x x equals to 1, y equals to infinity, and z equals to infinity. Making a reciprocal of it, we will get 1, 0, 0. And this set of plane, like if the silicon crystal is cut such that the top face is this plane, 100 plane, it will be called as 100 silicon. Okay. If it is cut such that the top surface is 111 plane, it will be called as 111 silicon. If it the top surface is 110, it will be called as 110 plane, 110 silicon. Okay, and if you closely see the structure, you will see that 111 plane have the most packed, like highest density of atoms. If we see the top surface, and as such, it have a very low etch rate. That means to etch it out, it is difficult for chemicals, and that is why this property is also used to make the uh, like etching of the crystal, silicon crystal, where we are able to etch one plane and other plane will stop it. Okay, so First is whenever we are going for cutting out or removing the uh, removing material from silicon, we are calling it as etching. Okay, we will see that there are actually two types of etching. One is surface and other is bulk. Okay, and we also call it as micro machining. Okay, surface micro machining, that means when we are doing these processes of removing some silicon or like removing some material from the no, top or bottom surface only, not going to the bulk. Whereas in bulk, we are removing, like I had told previously also, like suppose that we have a 3-inch wafer, okay, 3-inch silicon wafer round. So that will have a thickness of say 350 micrometer. Okay, if we are removing just 1 to micrometer, 1 to 2 micrometers on the top or bottom, okay, this we call it surface micromachining. Okay, whereas if we are removing some bulk amount, we are making a like through hole of say, like we are making a hole of 200 micrometer. We are making a membrane kind of structure, and that depth is say 300 micrometer, or we are making a hole throughout the surface to pass some to make some you say microtubes and all of say 350 micrometer or okay, that we call as bulk micromachining. Okay, so how this is done, to say it is very easy, but to deal with such thin structures, and that also with very good precision, how this etching is done. Okay, so it is done by two processes. Either we can go for wet etching or dry etching. Wet etching, or also known as chemical etching, is the one in which we have some wet chemicals in which we are dipping our wafer, okay, and etching is done. Standard chemicals to etch out silicon is KOH, potassium hydroxide, or TEMA. Okay, these two chemicals are commonly used for etching out. Is any doubt still here? Is anyone?
No, sir. Okay.
Oh, fine. And that chemical TEMA, like its full form is tetramethyl ammonium. Anyway, you will just get it in the search lecture also, hydroxide. Okay, so nowadays TEMA is more common compared to KOHs because because of some advantages. We will see. Okay, other method is dry etching, which can be plasma etching, reactive ion etching, or deep reactive ion etching. All these are dry methods. Okay, it has high precision, better output, but again complex uh, complexity is high, complex mechanism, as well as you have to be like there is not much selectivity in this case. That means whatever comes, it will etch out. Okay, whereas this wet etching have good selectivity in the sense the same chemical is etching silicon, but it will not etch SiO2. So if you put, it will not remove other parts, as well as taking the advantage of this chemical property. Sometimes it is done that some specific doping is done that at this point it has to stop. Okay, so I'll be saying these are the two methods, wet and dry etching. So let's see wet etching. So the setup that we need for wet etching is simply a beaker, okay, a beaker in which we will put the desired chemical, like let's say QH, okay. Then we will dip our wafer inside it and it will etch out at the rate, at the specific etching rate, like whatever is the etching rate. But it is not always desired to etch out everything on the top or bottom, okay. So we will need to cover, like if this is the wafer, we want to make some structure here, like this, some structure here, like this, okay. So we don't want to remove each and everything on the surface, but we just want to remove this to some depth, okay. So to do this, what we do is that we cover the area, other areas, with some masking layer. We cover it with such chemical that it does not get affected by the specific chemical, say KOH. KOH will not remove this material, but will remove the silicon. Okay, so some common masking layers for this KOH and TIMA are SiO2 or silicon nitride, Si3 and 4. Okay, and we will see in the next section how we pattern this. Like even if we deposit it throughout, we have to pattern, like we have to first make that this part has to be open. How we do that, we'll see in the next section. Okay, so KOH etching is very fast, okay, but it has the problem that it is CMOS incompatible. Why? Because potassium and ions have a very bad effect on our semiconductor devices, since they are mobile ions and they will act as, like if they stick to the surface, they will increase or decrease the conductivity of the surface. That is why KOH is not considered CMOS compatible. So another solution is TIMA, okay, which is having a slower etching rate, but it's CMOS compatible. Plus, along with this, etch rate will vary based on temperature, the doping of the silicon, and crystallographic plane. If we are taking 111 silicon, 110 or 100, it will have different etch rates. But for a standard temperature, standard dope, like fixed temperature doping and a fixed crystallographic plane, the etch rate will more or less be same for most of the processes that you do. Okay. So when we are doing the etching, there are two way, two ways these chemicals can affect our wafer. One is either it can be isotropic, other is it can be anisotropic. Isotropic means ideally, suppose that we have this wafer, taking the side view of it, right? We want to make a structure like this. This is the ideal case. But if a chemical takes out, like is able to etch it out, it is not necessary that it will remove exactly in this direction and no removal in this direction, left, like horizontal direction. That is not possible ideally. Okay, so most of the chemical have some like anisotropy in this, like isotropy and anisotropy. Okay, they if it is an isotropic etching, it will be uniform in both the directions. So we will not get a sharp cut like this. We might get a cut like might get a circular kind of pattern since the etching in uh, we can say vertical etch rate is equal to horizontal etch rate. That will make it a isotropic etching. Isotropic means equal in all the directions. Here the problem is that we cannot have good feature control because if you will see this structure from the top, it will look different. But if you properly inspect, there will be undercuttings. You see here, there is some internal structure forming, internal hollow structure. So if you see from the top, it will just look like here. The cut is like this, but internally it is isotropic. In such cases, we have poor feature control. Whereas if the etching is anisotropic in nature, that means vertical etch rate it is much larger than horizontal etch rate. So etching will be in one direction, that is going just inwards. So we will get a sharp feature inward. Okay, this is much like less probable in case of wet etching. But uh, we have some other techniques to improve anisotropy. Okay, it produces sharp, well-defined structures. So, but in wet etching also there are some ways how we achieve anisotropy. One is based on crystal orientation, specifically when we are talking about KOH and TMA. Okay, these chemicals affect one crystal like 100 plane the most. Then the rate is slower for 110, and for 111 plane it is almost negligible. That is why the structure that will be formed will be, if this is 100 silicon and we want to etch out this part, the structure that will be formed will be slanted. Why? When it will reach the 111 plane, this will be 111 plane, it will stop there. And as such, we are able to control. And based this angle, anyone remembers what is the angle between 100 and 111 plane? Yes, sir has covered this in the lecture. Anyone? Yes, please.
54,
54,
54.
54. It is 54.7
Okay.
degrees. Okay, correct. Right. So this angle is the angle at which the etching will stop itself, since it is the property of the plane that it will not be able to etch it out. Using this property, we are able to design a lot of structures. Specifically, we already know that this angle will be formed, so we design our mask based on that understanding only. Like we'll suppose that we want a whole structure of this size, say 100 micrometer, and we know the angle that is 57.4. So certainly the extra opening should be there, that extra opening. So we design according to that only. We design that extra opening so that at last we will get 100 micrometer and it will stop there. So such things can be done. Other way is these chemicals have different etching um, what affinity towards different type of silicon, that is p type and n type. They will etch differently. So even to make it much sharper, what can be done is that we can have some doping in the specific regions on the boundaries as well as at the bottom. So it will etch out these areas, but when it will reach the specific doping area where it is not able to etch out, it will stop there. Okay, these are called edge stop layers. Okay, uh, we will see this. Okay, so one thing is that convex and concave corner etching. The corners that we are making from the mask, like suppose you see this one, this is covered one, and this area is what has to be etched out, what is being etched out. Okay, so we start with this mask layer. Okay, and this is 1110. Okay, this cut, and the top surface is 100. Okay, and based on this, like I'll show you how the wafer looks like when we buy. So for a 100 wafer, there is a cut, small cut mark on the wafer. That gives the orientation of 110 plane. Okay, based on that, you see all the calculations are made here. So all the parallel planes parallel to 110 will be 110. Per Again, perpendicular to it will also be 110. Okay. Now, when this mask is used, if we do etching, we'll see although the mask look much different, the features that we are getting are quite different than what mask look like due to the edge stop of at 111 plane. Okay. Second thing is that convex corners etch faster due to undercutting. If we have corners which are convex, like such kind of structures are there protruding, okay, they will be etching much faster due to an undercutting forming below them. Whereas if we have a concave corner, okay, they are more stable and retain their shape while doing this TMA etching. Okay. So yeah, I was showing this. This is the angle 54.7 degree between 100 and 111 plane. So what are the as I talked about, what are the common masking layers for KOH and TMA etching? They are SiO2, which is used for KOH, and silicon nitride, which is CMOS compatible and is more frequently used in TMA. For TMA etching, sometimes rigs are also used. Proper physical rigs are also used if we are going for bulk micromachining. So physical Teflon based structures, if we are going for say very big holes like say 400, 500 micrometer in size, this size we can make in physical rig also. In that case, physically it is just kept and mounted over the silicon wafer. That is also used for TMA etching if the sizes are big. If it is smaller, then we go for lithography and all that we will see in the next section. Other is boron doping layers. If we at dope with boron, the etching will stop at that point. This is another technique that is used to make the patterns. So heavily doped P-type silicon etches slower in KOH, whereas lightly doped N-type silicon etches fast. So using this property, we are putting boron as the edge stop layer. So as we have seen that for MEMS fabrication, there are two techniques. Two micro machining or removal of material, bulk, and surface. In case of bulk, mostly large regions of silicon are etched. For surface micromachining, thin film deposition and etching usually. So when we talked about etching, we are covering both bulk and surface. Based on our usage, we will do more or less. In surface micromachining, there is one more thing that is there, that is thin film deposition. Thin film deposition means we might be depositing some thin layer, say of silicon dioxide, say some metal layers sometimes, some silicon nitride, sometimes even we are depositing polysilicon, that means non-crystalline silicon. Okay, these are deposited using thin film deposition techniques. And if we talk about deposition techniques, there are two kind of deposition techniques, CVD and PVD. CVD means CVD, that is chemical vapor deposition. Okay. Other one is PVD, that is physical vapor deposition. Okay. We will not be able to cover all these, like inside CVD again, there are multiple types of CVD available. PVD also multiple types. Some common I can say sputtering, uh, thermal evaporation, and other again sputtering is RF sputtering, DC sputtering, magnetron, like a lot of things are there. CVD, LPCVD, low pressure CVD, then atmospheric pressure CVD. One unique thing is atomic layer deposition. Like there are multiple techniques. We just need to know for this course point of view, since it is small course. Okay, we cannot cover these things. These are covered a lot in like some courses of microfabrication now. All. If you want, I have also taught some courses in the previous semesters and all. You can check on my YouTube. There, all these techniques are detailed. Like we have done a lot of discussion. Many classes we have covered on CVD and PVD techniques. Okay, so briefly we can understand that CVD or chemical vapor deposition is techniques in which some chemical reaction will occur on the surface that silicon wafer we are taking. We will have some gas reactant or something that will come on the surface. Two things, they will react, they will make a product and leave the product here, and byproduct will go out. That is chemical vapor deposition. Whereas in case of physical vapor deposition, we will have the material to deposit. Say gold we are depositing. Okay, we will have the gold, and then we will just evaporate it, or we will remove it particle by particle and deposit over our wafer. Okay, each have advantage and disadvantages. Like the CVD processes are generally high temperature processes, since reactions has to take place. They will have volatile materials and all, but they have very good film quality, since they are the reaction is taking place over the wafer, and the wafer like wafer is covered uniformly in this case, and very good quality film will be made. Whereas in case of physical vapor deposition, since we are transferring the material, the adhesion might not be good. We but although like what we do generally, we are depositing some materials like mostly metals using PVD techniques, as well as some dielectrics also. We are getting adequate adhesion, but it might not be good for some very high quality uses like gate dielectric and all. So it depends on our users. Okay. So any questions still here?
Sir, at the end of the class, I want to watch any video related to etching process, sir.
Okay. Etching process. That also you will get there. Like if you see my channel, in
Okay, sir.
the previous semester also I took one course, and before that
Okay.
there is one another course. Okay, in all these courses, they're etching all these techniques, like since that is semiconductor fabrication techniques, all these are discussed in details. Here, since we are just talking about how it is made, this course is like limited to how sensors are made and a brief
Okay,
introduction.
sir.
You see, the name itself is a brief introduction,
Yes,
right?
sir.
So it is not going very much deep into these processes, but you can see all these are available there. We have discussed all this. Okay. So now let's come to the practical point of view, how we start. Okay. We have seen these techniques, right? Now let's see how practically these things are done. Some methods we will see some practically how it is done. So to start with, first we will see how we select a wafer. Okay, how a wafer looks like. Though some of you might have seen a silicon wafer. Anyone who is well aware or have seen a silicon wafer? Yes. Hello. 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 Am I audible? Yes. Can anyone confirm? Am I audible or not? Okay. Fine. So sorry, there is some power cut here. So wait. Start it. Yeah. So my screen is visible. Hello. Can anyone unmute and speak? The slides are visible. Hello. Yes. Anyone can anyone respond? Confirm. Vishwajit,
Sir,
are you there? Yeah. Yeah. Yeah.
I
Right.
missed the question, sir. Can you ask another time?
No, I am asking, are my slides visible now?
Yes, sir, visible.
Okay. So let's continue. Okay. So So let's start with the basic, like how we start the process. Okay. To start with, we take a silicon wafer. Okay. So how a silicon wafer will look like? A silicon wafer will come in such a box. Okay. Or if you are buying some single silicon wafer, it will be in such single boxes. Okay. So first we have to identify what kind of wafer it is. Okay. So if it is a 100 N type wafer, there is no pure wafer available. Okay. Wafers are, if you get deep into the wafer fabrication process, like how these wafers are made, you will understand that there are two processes, CZ and FZ processes. Okay, in both of these, the doping is done in the uh, starting stage only. So the wafers that we are getting, we never make like in general, intrinsic wafers are not made. Wafers are either made generally N type and P type. Specifically, if you need a pure intrinsic wafer, what you can do is that either you can do equal amount of N and P type doping and it will just become intrinsic for for from the point of view of conductivity and all, or in such cases special special not fabrication, we can say special production processes will have to be used. That is why most of the wafers that we buy or we get are N type or P type. Okay, so how do we identify that what is its crystal orientation, that is what is the top layer, and what is its doping? So you take out this wafer. Certainly you don't have to touch with your hands. You have to use gloves and tweezers to handle these wafers. Okay. So first, if you see, there is one big cut mark and one small cut mark, and that also opposite to each other. Then it will be a N type 100. 100 is the top surface. This will be 100. Okay. Second is, if it is having both secondary and primary flat, but at perpendicular to each other, that is, they are separated by 90 degrees. In that case, it is a 100 p doped silicon wafer. Then, if it is just adjacent to each other, it is a 111 n type silicon wafer. And if it is just having one primary flat, it is 111 p type silicon wafer. These are most common 100 and 111. 100 and 111 silicon wafers are common, and you can go for N type or P type. In general, what I have seen from my practical experience is that we, the most common one is 100 N type wafers we take. Okay, or sometimes specifically for MEMS, 111 planes are also taken. Okay, so we will take this. Okay, yeah, I was saying that. If you see the process, right? So it start from this, like such a structure, and such ingots are made, and then they are cut, sliced. This whole process that you can see details in some microfabrication lecture. Uh, we will not be covering this. CZ and FZ processes are there to fabricate this. And one important thing is there, which I have, like these are not that relevant for this courses, but this one is relevant in the sense that what kind of environment is to be used for fabricating these devices. Since we are talking about very small devices, micro devices, right? So they have to be processed in special environment, that is specific clean rooms. We are doing fabrication in clean room. Okay? In clean room, that is where we are maintaining some cleanliness standards. What is the maximum allowed particle size in that room? How many total particles can be there? All these are controlled. It has a very good laminar flow. Fully controlled environment is used. Even people wear such protective gears. Everything is protected, gloves and all. These things are done. So we have a wafer. We take the wafer and then we start our processes. Then, what are some of the common challenges that we face when we are doing the silicon etching. Okay, since we have seen that theoretically how it will be done, but when we do the etching process, what are the limitations? What are the problems that we face? One is it has limited resolution. If you compare with dry etching, resolution in the sense how sharp images, how smaller features can, like what are the smallest feature that can be etched out, that is limited for wet etching. Second, we have seen convex corner undercutting, and when we are going for nanoscale MEMS or NEMS, okay, it is not suitable wet etching. That is why for MEMS fabrication techniques, deep reactive ion etching, hybrid MEMS integration, and bio-MEMS advancements are now like being used frequently. As well as if we see about deep reactive ion etching, it is plasma based. We are creating plasma of specific gases, generally fluorine based gases, which is used to do the etching process and multiple times. When we are talking about RIE, it is plasma based, and deep reactive ion, that means once it is done, then again it is masked, it is covered with some layer, then again reactive ion. So multiple times of reactive ion etching is done. That is deep reactive ion etching. So we saw that we we take the wafer, we are now ready to pattern it. Either say, if we are going for some simpler structures, we will go for wet etching. If we are going for some complex structures, we will go for reactive ion or deep reactive ion etching. Okay, but before going to this, we need to pattern. We need to uh, need to put mask. Okay, that means we need to define the etching patterns. Okay, and how we do that? We do that using lithography techniques. And one of the simplest lithography technique is photolithography, where we are using light as the patterning source. Okay, so to start with, let's see this small video. I have taken it from YouTube. Okay, yeah. Are you able to see this video? Yes, anyone? Yeah. So if you see this video, you see a painter is trying to paint some patterns, different patterns, one above another, and he is using different layers to pattern this. And in all these layers, there is one common thing. If you see on the top and bottom, he's using some cross marks, okay, to match them one pattern above another. A very similar technique is used for photolithography, in which such small patterns, if you see these small, very small patterns, they are made, but they cannot be made directly using paint and like such big stencils or masks. So what is done is that a uh, a light source is used to pattern this. Okay, so if we define what is lithography, it is a printing technique that involves the use of a flat printing plate or mask. to transfer an image onto a substrate. So first we will have to have a image of the pattern, like what pattern we want to make, that we will have to have, and that we can have on a mask or a glass surface like borosilicate or washed glass on which it is already made. First we make the pattern over a mask, okay? Then we transfer that pattern onto a substrate such as paper or silicon. The term lithography means stone writing. That is, earlier this technique was used to write things over stone, like such masks were used, and then from the cutout, like they will just paint it and it will be printed over the like stones. Okay. In modern times, lithography is used in various applications, including printed material such as books, newspaper, magazines. So, in case of integrated chip or semiconductor fabrication, or you can say MEMS, we use two types of lithography. Photolithography for larger surfaces, or larger feature size, larger in the sense micro, and around, yeah, starting from 1 micron above feature size, we go for photolithography. For sizes lower than this, we go for electron beam lithography, here, which is a bit complex and will not be covered here, but we will be discussing. The basic principle remains same for any lithography technique. So we will be discussing a bit about photolithography technique. So how this photolithography works? Yeah, just let me change the action. Yeah, you are able to see my slides, right? Let's get active. Yeah, hello. You people are able to see my slides.
Yes, sir.
Okay. So when we talk about photolithography, it's a process used in microfabrication to transfer patterns onto a substrate using light and photoresist. So here, photoresist is something that is playing great role. That is a photosensitive material. That means that a material that responds to light, you can say. Okay, so we'll see how this is done. So this I have taken from a course, nanotechnology course, Duke University. So these videos are snippets from there because actually it is quite difficult to film the actual photolithography process here, mm, because we cannot use flash and the light sources can disturb our process. So I have taken one from a already available course. Okay, so to start with, we have I think there is, yeah. So on this silicon substrate, the basic principle is there that a photo mask will be used. It will have the pattern over it. Then we will use a light source to transfer this pattern onto our, like this is metal pattern made over a glass transparent, like the other area are transparent, just the part that we want to pattern is uh, opaque. Using light, we will transfer this pattern onto our wafer, although it is not possible directly. So we will use a material which will first have this pattern, and then once that is there, uh, that photoresist will have the pattern, and then we will use that mask to pattern our material. So the process is like that we prepare the substrate, we apply photoresist over it, expose the photoresist to light, develop the photoresist, etch the substrate, remove the other part, and then we remove the photoresist since its work is done now. So one of the starting element is the mask. Okay, a mask will look something like this. It is made using specific software. Okay, uh, like here we use Edit and some Clavin, such softwares are there. Okay, in which we design this in our computers, and then we send it for processing, like we send it for printing to the specific labs. In India we have 3 4 facilities maximum, I think, where we can make, or like we can make these masks. One is in CSIR Siri Pilani and ISC Bangalore. These two I know. There are very limited such specialized systems where we can make masks. Even in our IIT Jodhpur, we are trying to make mask using laser writing and all. Okay, so it is made there. First, we make the software, like we make the mask using software. What patterns we need, we send it to our vendor. They will make this mask for us, and they will send the mask like this. It will have a glass surface with our pattern made of chromium, or uh, mostly chromium. These patterns are made with chromium. Okay, so that is opaque part, and the other are transparent part. So first process is application of photoresist. Okay, so we will put our wafer over a uh, flat flat surface with a flat chuck, we say. Over it we will pour photoresist, and we will rotate this whole wafer at a very high speed, in generally 3000 4000 rpm, and then this photoresist will cover it uniformly. Okay, so if we talk about photoresist, again they are of two types, positive and negative. Okay, positive will have like the light, wherever light falls, in case of positive photoresist, that part will be removed. In case of negative, it is opposite. Where light falls, it will remain. Where light doesn't fall, it will be removed. Okay, so if we see, if we cut the wafer, it is like we have the silicon wafer over it. This photoresist will be 1 to 20 micron thick. Okay, then comes the light exposure part, where we will use our specific setup, which we generally call as photolithography setup. Okay, so we'll put the mask in this setup, and then light will be UV light of 365 nanometer is used. And what it will do is that it will expose these areas which are not, like, the non-dark area of the wafer will be exposed, and we will get the pattern. Now, the area that saw the light after having photoresist, the area that saw the light is now able to dissolve in a specific chemical called as developer. Okay, the developer will be made specific to our photoresist. Okay, so we put it in developer solution, very similar to what used to be done in case of negative films uh, some 10-15 years ago. How we develop negative films, it is just done like that. In a dark room, we put it inside the developer. We, not dark room, yellow room, it is of having yellow light, that will remove the extra area. So, and then after this we will just wash it using DI water and blow it dry. So if you see, the starting wafer used to look like this. This is a silicon wafer. On it, some material is coated. In this case, gold is coated here. And then after the whole thing is done, whole patterning is done, these are the patterns that you see. Okay. If you want to see the whole process, it is like this, that in this yellow room, this wafer, coated wafer is taken, and then this is how photoresist coating is being done. So this is the chuck. It will have a vacuum chuck which will uh, just hold this wafer using vacuum. So we put that over it, put the wafer over it. It will just hold it, okay, and then photoresist is poured over it. Yeah, it is first fixed, and then the specific speed we want, like 4,000, 3,000, that will define the thickness of the resist coating. This port, and then it will be run at a very high speed that will coat it. Then to dry it, actually, it is just baked for some time, baked in, just heated at a specific temperature for some time so that it is dry. And then this is the mask that is fed into the system. Yeah. So since this UV light we cannot see directly, this whole process is done in a closed surface. You can see that just some reflection will be seen, bluish colored reflection. The whole setup comes, yeah, it exposes. Once this exposure is done, this again, this will not be infinite. It will be fixed for the time, since that will again depend on the thickness and the type of photoresist we are using. Then it will be developed, just like film development in old days, analog films. Okay, so in the developer solution, this will be put. So that will remove the area that have the exposure. Now it is cleaned and dried, cleaned using DI water, dried. So you will see the pattern is now transferred over it, and then it is inspected, see, and then the etching process will be done. So suppose that we want to remove this gold that was deposited, but we want to keep the specific areas that was the pattern. So now this photoresist has covered those specific areas we want to keep, other areas are open. If we take it and put it in the gold etchant, that will remove the gold, but leaving the areas that were covered with photoresist. So we will now have gold covered with photoresist left. After this whole work is done, then we will uh, put this whole thing in acetone, and that will remove the remaining photoresist, and we'll get the gold pattern. Okay, so this lithography is the process of patterning this. Okay, so any questions still here? Any doubts or anything you are not able to understand? Yeah, anyone? Any doubts? Anything you'd like to ask? Yes. Okay. You are able to see my slides? Anyone can respond? Yes, Siddhant Chauhan, you are able to see my slide? Are you there? Hello? Or, anyone? Vishwajit Mandal, Vinay, anyone? Hello? Can anyone respond whether I am audible or not?
Sir, audible, sir.
Okay, you are able
Sir,
to see? Yeah.
uh, one
Okay.
point, sir. Between the 100 and 110 planes, the
Mhm.
bonding, whether single bonding or double, one topic is have to be covered, sir.
Yeah, that bonding part, that actually sir have already covered, no?
Yes, yes, sir. Some just clarification, sir. Some
Okay.
dangling bond or etc. Something is in us. So we can
Mm.
get the clarity from your slides, sir.
Okay, so what I will do is that I will make some slides over this for the next week. Okay, I'll include that in the next week. Fine, because I have not made those slides for today.
Okay, sir. Okay, sir.
Yeah, for how the what is the difference between the bonding and this of the different planes, that I will put and we will have a small discussion over it. Fine. So any other questions? Any other doubts? Anyone? Okay. So let's uh, do some questions related to the topics covered in the present class. What is the crystal structure of silicon? FCC, BCC, diamond cubic, or zinc blend? Yes, anyone? Yes, please. Anyone?
Sir, is it FCC?
FCC. Okay. Any other answers to this? It is diamond cubic, which is very similar to FCC, but FCC don't have a covalent bonding. Okay, so it is diamond cubic lattice, which have a structure similar to FCC, but it is having some covalent bonding, which is different, a bit different. But if you just see the atomic orientation, it will look like FCC. Which crystal plane have the slowest H rate in QH? 100, 110, 101, or 111? Yes. This we have been discussing throughout the lecture, so I expect you people to answer, please. Yes, anyone? It is 1-1 plane as it is densely packed, making it more resistant to etching. And which one will be the fastest? It is
100, sir.
100 plane is the fastest. Okay. Why is
Sir,
TIMA? Yeah,
resistance, more resistant means breaking the
bond.
bond itself is difficult, sir.
Yes, breaking the bond is difficult. Okay. Now, why is TIMA used instead of KOH for CMOS fabrication? Is it due to lower cost, smoother etching, no metal contamination? Both B and C. Yes, anyone?
I
Which
think D, sir.
D, both B and C. As we saw that compared to KOH, TIMA is having smoother etching as well as there is no potassium. Like potassium ion is the problem in case of KOH. Okay, so this metal contamination is not there. Metal ions, if they get into the semiconductor fabrication system or CMOS fabrication, they will cause change in the conductivity, and that is why KOH is not preferred in case of CMOS fabrication. It is not compatible, whereas TIMA is not having the metal contamination. So both B and C. Which equation governs the silicon etching rate? This sir has covered. Yes, anyone? Arrhenius equation, Bernoulli's, Gauss, Newton's second law. Anyone?
Sir, I have not watched this video, sir.
Okay. It is the like even if you see Bernoulli's, Gauss, Newton, like these are not related to etching rate. And Arrhenius equation is the one that defines the silicon etch rate. Okay, where the etch rate depends on activation energy and the temperature. You saw that these are temperature is one big factor that will determine the etch rate, how fast the etching will happen. Okay, suppose that we want to do some faster etching, we can have higher temperature, but again it might need to some like, uncontrolled etching. That's why specific temperatures are used. Okay. What is the angle between 100 and 111 plane? 30 degree, 54.7, 90 or 75.4? Yes, anyone? This number we have discussed. Anyone? Remember we discussed about this 100, then 111 plane. What is the angle? Yes. Come on, anyone? Vinay, are you there? Vinay by Vinay. Yeah. Are you there? Or Ayush Gowda, are you there? Don't be shy. This is instructions. Yes, Vinay. Yeah. Please. Are you there? Hello. I'm not able to hear you. Vinay. Okay. So the angle is 54.7 degrees. Okay. That is a natural angle formed due to anisotropic etching in 100 wafer. And that is why we plan the mask according to that only, that we will have a 54.7 degrees sloped angle uh, between the 100, 100 and 111 plane. And that is why while def- have like while defining the features we do this calculation, like how depth, what will be depth. So such that if we want to have say 100 micron, say 100 micrometer length square inside. Okay, so we do a calculation like this, that this angle will be 54.7 degrees. Okay, so if we see this triangle, again this will be 54.7 degrees. So what extra width will be required? Say this is at say 10 micrometer depth. So what will be the extra um, value of the like opening we have to keep? So that will be whatever this comes d. So both sides. So 100 plus 2d will be the length of the mask, that length of the mask opening that we will keep. And as such, we will get a pattern like this. Such things we have to do while making the mask. Such calculations we have to take care of. Which factor primarily determine the etch rate in silicon wet etching? Etchant concentration, temperature, doping level of silicon, or all of the above? Yes, anyone? Ayush, are you there? Yes, anyone like to answer this? Which factors primarily determine the etch rate in silicon Wet etching?
I have seen one point, sir, in the notes where it is related to temperature, but here it is primarily means is it depends on the chemical equation like the concentration. I heard out, sir.
Concentration, if you see the Arrhenius equation, it is having all these like etchant concentration as well as temperature. Then we talked about doping level of silicon. That also determines the silicon wet etching. Okay, so in fact, all these factors are responsible for determining the etch rate. Equally, we can say it. They all have primary roles in determining. Even though you might have an adequate temperature, but the doping level of silicon, suppose that it is such that it will not, so that will become the limiting factor. Like in chemistry, we know that the slowest rate is the determining rate, right? Like that, whatever will be the limiting factor. Suppose that the everything is perfect, but temperature is too low for the etching to happen. In that case, it will be fully dependent on temperature. Okay, so whatever will be the critical one will determine the uh, etching rate. All of these will have like the etch rate will have dependence over all of these, like chemical reaction rate, temperature, which is given from RNS dependence, as well as doping. Doping defines the material solubility, how well it will be soluble or not. As we saw that highly doped N type is like highly doped boron is not easy to etch out. Okay, so that is the reason that it is used as a etch stop layer. If a silicon wafer has an initial thickness of 500 micrometer, and etched at a rate of 1 micrometer per minute in QH at 80 degrees Celsius. How long will it take to etch through the wafer? Yes. Yeah. So to etch out 500 micrometer at a rate of 1 micrometer per minute, how much time will be taken? Yes, anyone? It is saying that the thickness is complete 500 micrometer, and we want to create a hole throughout. And this KOH is etching at the rate of 1 micrometer per minute. So it is removing 1 micrometer per minute. So what will be the etch rate? What will be the time to etch it out?
500 minutes, sir. General
Five,
question, sir.
yeah, 500 minutes. Okay, since it is removing 1 micrometer per minute, so it will take total 500 minutes to remove 500 micrometer. Why does the 111 plane exhibit lower etch rate in KOH etching? Due to higher atomic density, lower bond energy, fewer silicon atoms per area, or weak etching reaction? Yes, anyone?
That is the yes, sir. Higher
Is
atomic density.
higher atomic density, and we have seen that third is directly wrong, since in fact 111 plane is having the highest atomic density, not the fewer. So fewer silicon atoms per unit area, that is not a correct answer. Okay, so it is higher atomic density, giving more resistance to etching reaction. Which etchant is commonly used in deep etching of silicon in MEMS fabrication? HF, TMA, xenon fluoride, or HCl? Deep etching. So we are talking about deep reactive ion. Anyone? I think you people have not covered that area. See the lectures. Sir is covering some parts. Since this is like a brief introduction, you can say, Sir is going not covering very deep into the processes, as that is not possible for a short course. But there are some points which are actually needed for the course. To understand what is happening, we have to cover those. So xenon fluoride. Remember I talked about fluorine-based plasma. Okay, so that is used for highly selective and isotropic uh, etching properties. HF is not used since it is highly, like, it is very volatile material, as well as it is liquid in uh, liquid, and it is acidic. That's why it is not preferred. So xenon fluoride plasma is used in deep reactive ion etching. What is the role of isopropyl alcohol in KOH etching? So it has been discussed in the lecture that isopropyl alcohol is used along with KOH. Okay, so it increases etching rate, reduces surface roughness, removes contamination, or enhances convex corner etching. Yes, anyone?
I think it will be like a moderator and it increases the etching rates, sir.
Yeah. And how it does? It does by increasing the surface roughness, by reducing bubble formation and surface defects. Okay, so it reduces surface roughness, and like rate is again determined by the concentration of KOH and all. The etch rate will remain same, but increasing the surface roughness, it will facilitate some surfaces like which, although theoretically we say that this etching will happen and all, but when we practically do, some parts will not etch out. The reason can be that they are smooth enough and they are not letting the chemical reaction to happen because that surface is not letting that KOH to stick to the surface itself. So in such cases, IPA helps. IPA reduces the bubble formation and surface defects. What type of micromachining uses KOH and TMA etching techniques? Bulk micromachining, surface micromachining, dry micromachining, electrochemical etching. Yeah, anyone? For bulk micromachining, we are generally using QH and TMA etching. For surface micromachining, although silicon removal is very rare, but for bulk, QH and TMA is most preferred one. Okay, and dry micromachining, like, there is nothing like that. Although dry etching techniques are there, like reactive ion and deep reactive ion. In that we use xenon fluoride or the fluorine and oxygen based plasmas. What property of silicon nitride makes it a good masking layer for KOH etching? High selectivity, low etch rate, thermal stability, or all of the above. Remember, KOH etching is done at a higher temperature, say around 18 degrees Celsius. Okay, as well as some heat is produced. So, what will be a good mask? A good mask will be one which protects, which does not etch itself, which has which is resistant to etching. Okay, so first thing will be lower etch rate. Second, it should be stable at different temperature and have actually high selectivity or lower etch rate is almost the same thing. That is having high selectivity. So high selectivity in the sense it will not etch this. Uh, KOH will be more selective towards silicon and not towards silicon dioxide. So highly resistant to KOH, thereby stable and provides good selectivity, making a excellent masking layer. And sometimes this is even used as passivation layer. Passivation layer is the one to protect. Once the whole device is made, it is covered with silicon nitride, except for the connections we have to make, so that the whole these devices are not affected by external influence. Like even we talked about Stixon and all, it will protect from Stixon and these things. Why does convex corners undercutting occur in anisotropic etching? Faster etching along 111 plane, unprotected sidewall, etchant diffusion effects, or secondary etching reaction. Yes, anyone? Okay. So convex corners expose 111 and 110 planes both, which etch faster compared to uh, 111 planes. And as such, undercutting effects are then. Undercutting means that we want this mask, we have kept this mask on the top, and we ideally what we want that the structure will be like this. But the structure that is forming is somewhat like this, okay, or somewhat like this. So this area, the hanging mask area, that is called as undercutting. Okay. In case of uh, convex corners, that is protruding corners. These corners will have both 100 and 110 planes, which etch faster. And as such, they will lead to much faster instead of since these two planes, this is 100 and 110, they will etch faster. So by the time it will reach the 111 plane, that will be somewhat slanted to this. Okay, extra etching will have been done. So it will be rounded and like then a flat surface will come. As such, we will see higher etching at convex corners. What is the primary advantage of anisotropic etching over isotropic etching? Yes, anyone? Faster etch rate, better directional control, no undercutting, etches all crystal planes equally. Isotropic means equal in all directions. So, anisotropy, what is the advantage of anisotropy? Yes, anyone?
Then better directional control, sir.
Better directional control because here it will be in one direction since it is anisotropic. Although there is no perfect isotropic etching, no perfectly anisotropic etching, there is a factor called anisotropy A that is defined by vertical etch rate by horizontal etch rate. Okay, so higher the anisotropy, better for high aspect ratio processes. So anisotropy etching provides high precision control due to selective etching of crystal planes. It is not that 111 plane will not etch at all. It will, but it will be much slower compared to what it is doing to the 100 and 110 planes. A silicon wafer is marked with a primary and secondary flag. What information do these provide? Crystal orientation, wafer doping type, both, or none of the above? Yes, anyone? Yes, please. This we have seen. In fact, I think in today's lecture we have discussed this two times. Anyone would like to answer?
Yes, sir. Crystal orientation and vapor doping type also, sir.
Yeah, both.
See,
Because see, because by seeing the positions, we can say that whether it is 100 or 111 type, or it is yeah, P type and N type. Okay. How does doping affect the silicon etching rate in QH? It increases etching rate, decreases etching rate, has no effect, or depends on the etchant concentration.
sir, B, sir.
B. Okay. Yeah. Any other answers?
Sir, you have told boron type that
Yeah.
is acting as a H
H
stop
stop.
layer.
Yeah. So it is decreasing the etch rate. Since heavily doped silicon etches slower in KOH due to change in crystal lattice properties. Since it was uh, going faster because of its orientation, because of its structure. Now, when there will be a doping, it will be at a more stable state, so it will not be easy to dissolve and etch out. So that decreases the etching rate. Which MEMS applications benefit most from aspect ratio etching? Spect ratio, high spect ratio etching. That means very thick, deep structures without like high spect ratio means length is much depth is much higher compared to the size of opening. Unlike the isotropic ones or such. other structures we generally are able to do. Such structures, they have larger opening, lower depth. Not this, but this kind of structure. What applications they can be used of? RF MEMS switch, bio MEMS, or MEMS accelerometer. So all of these actually uh, use high aspect ratio etching, which is achieved using deep reactive ion etching. Okay, precise geometry and deep structure. So the same thing if it was for surface micromachining, it could have easily been done using wet etching. But when we are talking about some structures, even uh, smaller structure, but we need very precise aspect ratios. We don't want bulging on the top and all. We have to go to deep reactive ion etching or reactive ion etching. So there is no fixed rule that this kind of depth we want, we will go for wet or reactive ion etching. It will depend on what is the allowed permissible variations, how much opening we can have, or how well, like how better aspect ratio we want. Sometimes this aspect ratio if has no effect on our structure, why to waste too much of resource and time as well as cost over process like reactive ion or deep reactive ion. But if it is critical to the structure or critical for the sensor, we go for it. So the selection will depend very much over the uh, what you want, what is the effect of the changes, like will it have higher effect over our sensor or it will have negligible effect, and again then we will go for the cost effective method. But if even if like this cost effective method is good, but it will have some have very large implications over our sensor, we go for the we don't go then for cost effective method, but we go for a higher precision method like plasma etching, reactive ion etching, and such processes. What happens to the etch rate in KOH concentration? If KOH concentration increases beyond an optimal level, we are increasing the KOH concentration. So since it will get stronger, it will have more etching. That is common. But what if it goes beyond an optimal level? Will it still increase linearly, decrease, remain constant, or becomes unpredictable? A plot like this was made, right? Different concentrations, different H rate and all. Yeah, anyone remembers? Yeah. What happens to the H rate? QH concentration increases beyond optimal level. It will decrease. At very high concentration KH, etching becomes mass transport limited. That means uh, how much this material is removed, how well it is removed from the point of reaction, because then only the reactants will be able to reach to the target area, target surfaces, and as such, increasing it beyond the optimal level will decrease the mass transport and as such decreasing the reaction. Why is SiO2 a poor masking layer for TEMA etching? If we compare it with silicon nitride, for TEMA etching, SiO2 is not preferred much. Why? Is it due to low selectivity, high solubility in TEMA, poor addition, forms microbubbles? Yes, anyone? It is due to high solubility in TEMA, making it less effective as mask than compared to silicon nitride. Which of the following is a key limitation of wet etching in MEMS? Limited feature resolution, high cost, slow etch rate generates toxic byproducts. Yes, anyone? We have discussed that actually wet etching is more cost effective, so high cost cannot be there. It have very good etch rate, although sometimes we cannot even control the etch rate, so we have to slow it down, we have to dilute and all. Okay, so slow etch rate cannot be there. As well as most of the byproducts are not that toxic if we compare it with dry etching, like xenon fluoride and this. They starting from xenon fluoride itself, it is toxic in nature. Okay, the problem with wet etching is that it has limited feature resolution. That is, the aspect ratio is low. Okay, so is less precise than dry etching due to undercutting and isotropic effect, making it not suitable for small scale, high precision MEMS. Okay, so that's all. Any questions from here? Anything I would like to ask or clarify? Yes, anyone? Anyone would like to ask something?
Hello, am I audible? And what you were asking, crystal orientation, how this will affect, right? Uh, Venkat Lakshmi, you were asking, right? Hello.
Sir,
Yeah, crystal orientation. Specifically, what is the structure and what other thing you were asking?
covalent, the bonding,
Bonding. Okay.
covalent
Yeah,
bond.
that I will make slides and we'll cover that. Okay. So
Okay.
next topic is pressure sensor and accelerometer. So sir will be discussing in week 4 about some pressure sensor and accelerometers. This that is like a case study. Okay, that will be covered next. So anything else you would like to ask? Anyone?
Sir, in our India, whether we are constructing large scale microsensors, sir, or only for research purpose, sir?
At present, more like till some years back, we were mostly producing for research. Like we were just doing research and all. Now you see, government has taken a lot of initiatives. In fact, in last 3 4 years, we are seeing some companies coming up for manufacturing also. So we are like we have started some production level things, but yes, not to the level that is required.
Sir, is this manufacturing is quite different from the VLSA technology fabrication and this one different, sir?
No, no, very similar. Like clean rooms are same. Like you see, the fabrication facility will be the same. The processes are similar. Like I said, this is a adaptation of the VLSI and semiconductor fabrication only. So the processes are same. This plasma etching, surface micromachining, wet etching, all these processes are used in VLSI technology. It is just that the purpose has changed. Like in this case, bulk micromachining sometimes comes in play, MEMS. Okay, that again, lithography is still the same. The designing will be a bit different, the purpose will be different, but technology is same. So you can say a similar the same facility can be used for both the purposes. Yeah, any other questions? Sorry. Yeah, anyone? Okay, so let's conclude the class. So thank you all. See you all in the next class. Thank you.